Hi, thank you for being here. I am Yang Hao Lin. I work as a software engineer at ByteDance. Today, I will be introducing how we built an EP-scale feature store using Iceberg. So here's the outline of the session. Basically, we will be covering some backgrounds, then our optimizations and practices, finally the summary and outlook. So now let's turn to our first section, which covers the background and trends of machine learning datasets. At ByteDance, machine learning models are used very widely. To support the training of these models, we have established two major training platforms, a recommendation and advertising training platform, and a general CV NLP training platform. The recommendation and advertising platform trains tens of thousands of models every week, while the CV and NLP platform trains up to 200,000 models every week. Such a large scale of model training is supported by a massive amount of training datasets. Currently, in ByteDance's offline dataset storage, the total data has reached the exabyte level, with daily growth at the petabyte level. The datasets are both large and wide, with the largest dataset holding 150 petabytes of data. Also, every dataset has around 30,000 columns. This data is used to support the training of models for advertising, search, and recommendations, and it covers multiple business areas. It also supports the algorithm team in feature research and engineering, and provides a foundation for model iteration and optimization. So currently, the trends in machine learning at ByteDance and across the industry are as follows. Firstly, models and datasets are getting larger and larger. With the increase in model parameters, more and more training data is needed to ensure the accuracy and generalizability of these large models. Secondly, training computational power is increasing. In the past, training a machine learning model could take weeks or even months. However, today, with better model architectures and GPUs, we can complete the training process and conduct A/B tests in a relatively shorter period. And thirdly, feature engineering is becoming more automated and end-to-end. In traditional machine learning, feature engineering is a critical component, usually requiring a lot of manual labor, time, and effort to handle data and features. With the advancement of deep learning, however, we can now leverage its feature extraction capabilities to automatically learn features through simple data processing steps, and even simplify the process to just adding columns in a table of raw features, and then using deep learning frameworks to automatically learn and extract information. Overall, machine learning and datasets at ByteDance play an important role in the business operations. By establishing robust training platforms and accumulating massive amounts of datasets, ByteDance can support large-scale model training and optimization. Moreover, current industry trends indicate that the growth in model and dataset sizes, along with increased training computational power, are driving the development of machine learning, while the automation and end-to-end nature of feature engineering are being convenience and efficiency to model training. So through the trends I mentioned earlier, we can also identify some current challenges to achieve a cost reduction and efficiency enhancement. Firstly, there's a need to optimize the storage size of datasets to reduce storage costs. As datasets get larger, storage requirements and costs are also increasing, posing a challenge for large-scale model training. Secondly, the read throughput of datasets needs to be optimized. With the iteration of chip technology and the growth of computing power, the computational resources required for training models are also continuously increasing. However, if the read throughput of datasets cannot keep up with the growth in computing power, it will become a bottleneck, in the training process, which limits the effective utilization of computing resources. Therefore, we need to find ways to increase the read throughput of datasets. And lastly, with the aid of deep learning, feature engineering has becoming more automated and simplified. We can follow this trend to further enhance the efficiency of the feature research and engineering process. By accelerating the process, we can shorten the iteration cycle of model development. So following up from these challenges, let's now delve into the conventional methods for dataset storage. And conventionally, datasets are stored directly on HDFS, object storage, or Hive. This approach encounters performance bottlenecks when handling massive volumes of data. Due to the use of single-point list operations, scanning a large number of files becomes extremely slow. Additionally, when it's necessary to add columns or features, the use of copy on write has a significant overhead due to its nature of read-write amplification. This raises storage cost and also leads to unnecessary computation. The second method of storing datasets involves using conventional database solutions. This approach is more suited for handling smaller volumes of data. However, when dealing with massive data reaching PB and EB levels, it becomes problematic. Furthermore, since training nodes cannot directly read from the underlying database files, the read throughput will be limited by the database nodes. So building on our exploration of conventional dataset storage methods, let's consider the emerging dataset storage solutions based on data lakes in the next slide, with a particular focus on Hudi and Iceberg. So Hudi offers a emerging read method for column-level updates, which significantly reduces the overhead of adding new feature columns compared to the conventional copy-on-write method. However, Hudi's emerging read performance is not ideal, involving multiple format conversions and spilling to disk, which causes additional I/O operations. Additionally, Hudi does not support a native Python API, only accessible through PySpark, which is not very user-friendly for algorithm engineers. On the other hand, Iceberg, as an open table format, stores metadata of a table, including its schema, files, partitions, and statistics. So Iceberg's metadata storage and operations are scalable, which accelerates file scanning for large PB level tables. However, Iceberg's merging read feature also has some issues, such as the community version not supporting column level updates. And notably, Iceberg offers Python API support, which is a significant advantage for algorithm engineers. In summary, both Hudi and Iceberg are emerging dataset storage solutions based on data lakes, each with its distinct features and advantages. While Hudi has some performance issues and lacks Python support, its merging read method is suitable for feature research. Iceberg offers an open table format and highly scalable metadata, along with Python API support, providing a more friendly environment for algorithm engineers, though its merging read capabilities need enhancement. From this, we can see that common solutions often have their shortcomings and are not ideal. Ultimately, we decided to develop and strengthen our own solution based on Iceberg to address the gaps and meet the business needs for dataset storage and feature engineering. And this takes us to the next section, where we will be discussing our enhanced architecture at ByteDance based on Apache Iceberg, known as Magnus. So here's a diagram that shows the comprehensive structure of Magnus, which can be broken down into 3 layers. The top layer is the computing framework. It naturally supports ETL and data analysis using Spark, Flink, and Krypton, where Krypton is a hybrid serving and analytical engine at ByteDance. Magnus also supports various training frameworks. This includes Primus, which is our team's open source distributed training framework, as well as training frameworks as PyTorch, TensorFlow, and Ray. Users can choose the appropriate computing and training framework based on their needs. The second layer is the core of Magnus. It provides users with SDK and the metadata service. On the platform capability side, it supports various data management tasks such as data ingestion and maintenance. Notably, this layer introduces a high-speed vectorized merge-on-read engine based on Arrow, which can efficiently merge data and enhance read performance. The foundation of Magnus is based on an enhanced version of Iceberg metadata, which supports partial update, version management, fast file scanning, and other functionalities. The bottom layer is the foundation of the entire architecture, responsible for the actual data storage. It supports multiple file formats, including the columnar storage format Parquet, row-based format TF Record, and other proprietary formats. The platform encourages the migration to columnar formats, which can save storage costs by an average of 30% to 50% and improve read performance. Ultimately, these files are stored in HDFS or object storage to ensure data security and reliability. So overall, Magnus provides our users with various capabilities as listed on the slide. Some of them are natively supported by Iceberg, while others are unique enhancements specific to Magnus. In the next sections, we will mainly focus on these unique features of Magnus. So first, let's introduce the first core feature of Magnus, which is column level update and branches. As we have discussed in the data storage solutions, lightweight column update operations based on merge and read are key to accelerating the feature research and engineering process. Therefore, we initially developed the first core feature, lightweight column level updates and branch management on Iceberg. Iceberg has two types of files originally. One is the data file, which records newly added rows. The other is the delete file, which records information about row level deletions. Based on this, we introduced the update file, which records column level update information. To perform column level updates on a Magnus table, users only need to provide primary keys and data for the target columns, greatly avoiding the problem of read-write amplification and achieving lightweight column updates. And during reading, data files and update files can be merged to produce the complete rows. As for branches, Iceberg's tree-like metadata structure is powerful and well-suited to support data branching. When algorithm engineers conduct feature research, they can write update files to a branch, while the branch can still reference the original data files on the main branch. This ensures isolations between branches without affecting the baseline model that is training on the main branch, while it also avoids unnecessary data file replication. We also developed a Git-like operation for branches, which are merge, delete, and rebase. These branch operations are all based on Iceberg metadata, making them much lighter compared to data operations. Next, we will discuss how column level update and branches are widely used to shorten the feature research iteration cycles. The first application of update and branches is large-scale feature research. To accelerate feature research, we have widely applied update and branching within the process. In some business areas with multiple high-potential feature sets, algorithm engineers can perform parallel backfilling, research, and training on their respective branches. And once the research model metrics meet expectation, the user can submit a ticket to merge the feature set into the main branch. As for models that are already mature, most research features may not show significant effects, so the user may delete the branch. When such branches are deleted, data maintenance tasks will delete the files from these branches to save storage space. And furthermore, if the feature set requires further validation and research, algorithm engineers can rebase the branch onto the main branch to get the latest training data and repeat the update, training, and validation cycle. This application on large-scale feature research also presents some challenges, such as the issue of small files resulting from many update operations. Therefore, we deploy monitoring on number of files and perform compaction when necessary. Another application scenario is supporting multiple training objectives by reusing the same set of features through data branching. For convenience, we refer the training objective as labels. When advancing a new model, if there's a new label to be added, algorithm engineers only need to backfill the label column using column level update and can then directly reuse the existing features on the main branch. After a few hours of training, they can then start A/B testing to evaluate the model's performance on the new label column. Also, successful new features merged into the main branch can also be quickly reused across all labels with zero data copy. And ultimately, by using branching and reusing feature data, we have saved about 90% of storage space on some recommendation projects, significantly accelerating the research cycle for labels. And this concludes our introduction to the update and branches core feature. Next, let's take a look at the second core feature, which is the Magnus dataset. Magnus dataset is a high-performance merge-on-read engine. It is developed based on Apache Arrow. Although Iceberg community also supports vectorized reading with Arrow, it does not support complex nested types, while most datasets contains nested type data. So in contrast, the Magnus dataset provides support for these complex nested types. On ByteDance's open source training framework, Primus, Magnus dataset achieves approximately twice the read throughput compared to conventional vectorized reading. This ensures data reading is no longer a bottleneck in GPU training. Moreover, the output is in Arrow format, which can next conveniently interface with Spark, Pandas, and other APIs with a zero copy. Arrow also facilitates cross-language integration of the Magnus dataset, which we will discuss in the next slide. The Magnus dataset is implemented in C++ and utilizes Arrow, a cross-language memory format. This design allows computing frameworks implemented in various languages to use the Magnus dataset, leveraging the same merge-on-read logic. For instance, a C++ reader like Krypton can directly depend on the Magnus dataset. As for languages other than C++, after compiling the Magnus dataset into a shared library, Java readers like Spark and Primus can access it using JNI, and Python readers such as PyTorch and Ray can make calls via PyBind. This cross-language capability ensures broad compatibility across different computing frameworks. In some of our model training and data processing tasks, many training data can be skipped or sampled. We push down predicates to row group level and avoid unnecessary IOs, thereby speeding up the process. However, predicate pushdown is not trivial for Magnus tables containing partial column updates, because for a specific primary key, the value of a specific column can be distributed in multiple data files and update files. Only after merge on read will we know the current value of the column. Therefore, predicate pushdown cannot simply be applied on each individual data file or update file before merge on read. Our solution is to use a late materialization technique to do predicate pushdown for merge on read. Let's break down the process. First, we utilize Antler to parse predicate expressions. Spark filters are converted into a readable expression text and then transformed into arrow compute expressions. And next, our approach involves a two-pass reading process. In the first pass, we don't read the entire dataset. Instead, we only read specific columns, namely row numbers or primary keys, and columns that are directly relevant to the predicate expression. This targeted reading helps us identify the rows that meet the conditions specified in the expression. In the second pass, having identified the relevant rows in the first pass, we now perform a more focused read. We only retrieve rows that satisfy the expression by skipping row groups, and we only fetch the necessary columns. In this way, we achieve a predicate pushdown for Magnus tables with partial updates. Next, let's introduce the first application of the Magnus dataset. We have collaborated with other teams at ByteDance to switch the end-to-end memory format of offline training to arrow format for our major models, which has significantly reduced the use of memory and computational resources, avoiding many unnecessary memory format conversions and serialization overheads, and achieving substantial benefits. We have also made some arrow-based modifications in the commonly used Spark engine for data analysis and processing. It's important to note that we have also tried switching to arrow in online streaming training, but the overhead remains significant. A possible reason is that streaming data are processed individually, which is not suitable for arrow's batch-oriented form, thus leading to additional overhead. And the second application of the Magnus dataset is optimizing massive shuffles. When processing massive datasets, algorithm engineers spend a lot of time on data cleansing to improve model conformance. However, cleansing data often requires using shuffle operations, where common issues include shuffle failures and slow performance. In some common scenarios, the shuffle can be optimized based on column level updates and filter pushdown. So see scenario 1, for instance. If the user needs to join a petabyte scale large table with a medium-sized table, they cannot use the common bucket join due to different bucketing methods, nor can they use the typical broadcast join due to insufficient memory. In such cases, we can use the column level update operation to write the smaller table to a temporary branch of the larger table, converting it to the same layout as the larger table, and then push down the filters to read out the joint dataset, which will be very fast due to row group skipping. In this way, we avoided shuffling the petabyte scale large table. Similar for scenario 2, if the user needs to optimize model performance by scattering and deduplicating petabyte scale datasets, they can first read the key column only, assigning each key with a random partition value and an indicator of whether the key is distinct, then save the 3 tuple records as a small temporary table. Then follow a similar approach by writing the small table onto the larger table. Finally, use filter pushdown to retrieve the required data. Having the features mentioned previously, such as column-level updates and high-speed merge and read, is not enough. There are also some business scenarios that require multiple partial data streams to be directly and concurrently ingested into the lake. Partial data streams here means that each data stream only contains values for part of the columns and may not contain values for the partition columns. This scenarios depends on the next core feature we will discuss, which is partial upsert and global indexing. Through global indexing, we can determine whether any records with a specific primary key has already been written. If already written, we can locate its belonging partition. This guarantees uniqueness of the primary key across the whole table. For this part, we drew inspiration from Apache Hoodie's design. Besides supporting H-based global indexing, we also support H-file indexing. This means directly using H-base's underlying data format as an index and hosting it within Iceberg metadata, which optimizes performance and concurrency. Compared to other types of indexing, using H-file indexing reduces the need for extra components, reuses storage resources, and avoid issues with bursty read or write traffic. Looking at the entire writing process, Magnus looks up the global index to determine which partition and bucket a record should be written to. During reading, merge and read is performed on a bucket basis, ultimately restoring the whole record. And next, let's discuss the application scenarios for partial upsert and global index. Business scenarios such as risk control are likely to do large window joins between features and labels. These large windows here are equal to or greater than 1 month. Online joins with large windows require extensive computational resources, so offline joins by partial upserting to Magnus is preferred, which is much cheaper. In addition, we support concurrent partial upserts on the same set of keys, allowing dataset updates, label backfilling, and feature research to occur simultaneously. The core idea is to give users the choice to tolerate concurrent write conflicts, providing various merge and read logic to meet business needs. We have the first write win strategy, where the first entry remains, and last write win strategy. We also support strategies like concatenation to a list and custom merge and read strategies that tolerate concurrent upsert conflicts. For some other business scenarios that require strict serializability, we also support partition level and bucket level conflict detection. Furthermore, for upserts that flow back to earlier partitions, we perform compaction based on data temperature to avoid performance loss due to small files. And that's all for the core features of Magnus. Having introduced Magnus and its core features, we have also accumulated best practices for handling massive data sets in Iceberg. Let's move on to the next section and briefly discuss some of the key contents. The first best practice is feature deletion. In some cases, direct physical deletion of features may impact downstream tasks. So for such situations, logical deletion can be achieved by renaming the feature columns. Since the training side reads data based on feature names, the features become inaccessible after renaming. If any algorithm engineers find that this impacts the model, they can simply rename it back. If there is no impact after a period, the feature can then be safely physically deleted. Next, let's introduce the second best practice, which is rollback versus revert. When issues arise with the data source or pipeline, problematic features ingested into the lake can impact the effectiveness of the training model, leading to online failures. The common response to such situations is a rollback, where the problematic write snapshots are rolled back. However, this approach can also roll back subsequent normal writes, which may affect downstream training or data processing. Therefore, we developed a revert operation that allows specific snapshot operations to be undone at the metadata level without affecting subsequent normal writes, making it more friendly for downstream tasks. The third best practice is skipping and monitoring dirty data. Facing massive data sets, dirty data occurrences such as data loss or corruption are inevitable as the volume of data increases. Therefore, we support retries for dirty data, such as switching nodes for retries and supporting skipping only a certain proportion. To better manage the dirty data issues, we also utilize dashboards. These dashboards collect table-level dirty data counts, enabling monitoring and alerting to promptly address data quality concerns. The fourth best practice is big metadata optimization. Facing massive datasets, metadata also becomes big, which needs to be treated, slimmed down, and optimized, just like big data. For instance, in machine learning scenarios, the predominant method of reading data is by scanning, but not point queries. In such cases, we can remove a significant amount of column statistics recorded in the Iceberg metadata, effectively reducing metadata size, especially in scenarios with large wide tables, retaining only necessary information such as partition and primary key min-max values. This significantly reduces the time spent on file planning and avoids memory overloads in driver nodes. Finally, let's discuss the fifth best practice, which is metadata speed up. Traditionally, handling big metadata has often relied on single-point processing, which can be inadequate when facing large-scale metadata. In such cases, we can accelerate by pruning metadata files and also processing big metadata distributively. For jobs that rely on full table scans, such as compaction, we also use distributed planning to speed up the process and avoid out-of-memory issues. This concludes the best practices for handling massive training datasets at ByteDance. And finally, let's summarize the key points we've covered and look ahead to the future directions and potential developments for Iceberg at ByteDance. To summarize, we introduced the overall architecture, core features, and optimizations and practices of Magnus, an enhanced version of Iceberg. To briefly summarize the content covered previously, it includes three key points. The first is significantly optimizing dataset storage by using a columnar storage format and employing update and branch data reuse strategies. The second is accelerating read throughput with the Magnus dataset engine, which leverages Arrow's vectorized merge and read capabilities. The third is conducting large-scale feature research and engineering based on the capabilities of column-level update and branching. And at last, I would like to share some of our future outlooks on data lakes and feature stores at ByteDance. First, we plan to bring together our data lake and streaming systems. This means managing and interfacing both historical batch data and real-time stream in one unified system. And second, we are moving toward using next-generation data formats. These new formats will use better encoding algorithms and storage optimizations to help us access and process data faster. They will include quicker ways to seek data and better indexing support. And that brings us to the end of the presentation. Thank you for your attention. Any questions?
All right, thank you, Lynn. Great session. So we have some questions. I will moderate some. So first question is, any scaling experience to share with respect to support 30K columns? Any challenges you faced?
Schema change. You mean schema evolution with 30K columns?
Correct. That's the meaning. Yep.
Yeah. I guess we haven't encountered the bottleneck in schema evolution. When users want to add a feature column, he just he just do the schema update in the on the metadata at the metadata level. I think he means when adding a new column, how do we backfill data for this new column? I think this is the question. And we have already mentioned in our slides that we have implemented a column level update file. We use the column level update file to backfill the new column only. And later we do the merge and read to merge the data file and the new update file to get the full row. Yeah.
Okay, thanks. We have a second question, which is how do ByteDance manage rebasing against open source Apache Iceberg project?
Manage rebasing against
Meaning you probably have a fork of Iceberg where you add your features. How do you deal with rebasing on new releases and version of Iceberg?
Yeah, actually, so at ByteDance we are using Iceberg 0.10, which is quite an old version, and we were still working on this, trying to catch up with the progress of the community. Also, yeah, we're still exploring on this.
Okay, good. Related to that and to the Apache Iceberg project, do you have any plan to contribute any improvement or Magnus feature to Iceberg at some point?
Yeah, I guess, yeah, we are willing to contribute these features, but I think some of the features may not be quite compatible with the community standard. So we're still looking into it. For example, the update files and supporting partial upserts. These will really break the spec of Iceberg. So it's kind of hard to merge it into the community. We're still looking into it.
Yeah, okay. Yeah, you are using a pretty old version of Iceberg. I mean, the latest is 1.51, so 1.2 actually. So yeah, we have a lot of new features and changes. So yeah, that's challenging, I guess, to rebase and also probably preparing potentially pull requests and so on. Yeah, but yeah. Any other question from the chat and from the attendees? We are almost at time. So yeah, just to wrap up, thank you again for joining us. Thank you, Lynn, for your great session. Very interesting to see that.